This is video 1.1, absolute value parent transformations. The instructions at the top of the page tell you that the absolute value parent function is f of x is equal to the absolute value of x. We are going to utilize the graphing calculator today, and so the instructions also tell you how to graph it. You're going to first go to y equals, and you want to go to the number menu by hitting math. The math key is right here under the green alpha key. And if you will right arrow once to the number menu, choice number 1 is absolute value. You'll enter an X between the absolute value bars. The X key is to the right of the alpha key. Press enter, so we have y equals the absolute value of x. And you could hit the graph button then to get the graph. Notice in my four pre-printed examples, I have it drawn because we want to specifically talk about transformations of the absolute value parent function. That would mean how it shifts when we change parts of the equation. The parent function, as you know from filling out your chart earlier, the absolute value parent function starts at the origin at 0, 0. They are straight lines on either side, the right side having a slope of positive 1, the left side having a slope of negative 1. And then if we start adding and subtracting things to the parent function, or the most basic function, it starts to change what the graph looks like. So for our first example, we want to work with the absolute value of x plus 2 and the absolute value of x minus 3. Notice this plus 2 and minus 3 are outside of the absolute value bars. So I'm going to go back to my function here, and I'm going to scroll all the way to the left so that the cursor is blinking in front of the y and press enter. That will make my original function, or my parent function, a bold line so that I can delineate it from the transformations. Go down to the second function, and I'm going to make this the equation in the example. So I'm going to hit the math menu, right arrow to the number, choose absolute value, and put an x in my absolute value bars. Then right arrow to go out of the absolute value bars and put in plus 2. So now I have the first example. I'm going to hit graph. There's my parent function. Notice that it's now bold. And there's my new function. And what you hopefully notice pretty quickly is that it's been moved up 2 units from my previous function. Everything else is the same. So I'm going to graph that real quickly. I'm going to shift everything up 2 units. So my new vertex is at 0, 2. What was 1, 1 is now 1, 3. What was 2, 2 is now 2, 4, etc. My slope is 1 on the right side of the graph. And on the left side of the graph, my slope is negative 1. I'm sorry, this should be 3, 4, 5. I apologize. Turn this. It will be a little neater as I go. This is my first run at a video this year. It takes a little time to get back into the swing of things. Alright, so now I want to see what happens when I've changed that plus 2 in that second equation to a minus 3 instead. There's my parent function showing up in bold, and notice that the new one has been shifted down 3 units compared to the original, or the parent function. So down 3 units, the slope is still positive 1 here, and the slope is still negative 1 here. Let's see if my green pen is going to cooperate. So, if we try to put this in words, the absolute value of x plus 2 created a vertical shift up 2 units. Vertical means it moved up or down. And then the minus 3 created a vertical shift down 3 units. So if you're asked to describe the transformations, you want to make sure you're using the words vertical shift if it's moving up or down, and then actually tell us, does it go up or does it go down? In our second set of examples, notice the minus 2 plus 3 are inside absolute value bars now. I'm going to go back to my calculator and change my second function so it has minus 2 inside of the bars, nothing outside of the bars. There's my parent function. There's my new function. Notice it is shifted to the right 2 units, and this might be a little bit counterintuitive for you that subtracting inside the bars would move it to the right. Let's sketch this graph. 2 units to the right, everything else stayed the same, so a slope of 1 on the left and a slope of 1 on the right. Sorry, negative 1 on the left and positive 1 on the right. So this was a horizontal shift. If it shifts left or right, we're going to call it horizontal. So this was a horizontal shift right 2 units. And you can probably anticipate at this point that if a minus moves it to the right, a plus is going to move it to the left, but we'll put it in the calculator to be sure. Change the -2 to a +3 and hit graph. There's my parent function, and there's my transformed function. It did in fact move 3 units to the left, so graph that real quickly. Notice that I'm able to do this very fast because the only thing we're changing at this point is the vertex. We're only doing vertical and horizontal shifts so far. So if I were to describe this, it is a horizontal shift left 3 units. Alright, moving on to example 3. We do have 4 of them total in case you're wondering. Now we have a number in front of the absolute value. We have a 3 for the first one and a 1/2 for the second one. So I'm going to go back to my y equals, and here I'm going to insert a 3 in front of my absolute value of x, delete the stuff that's inside, and hit graph. Here's my parent function. There's my new function. Notice the vertex is the same, and you could pull up a set of points if you needed to confirm that the vertex is the same. But where it was 1, 1, it's now 1, 3. And where it was 2, 2, it's now 2, 6. And 3, 3 is now 3, 9. Notice that the y values have increased by a factor of 3. That's what we call a vertical stretch. You've made it taller and thinner. And I like to use the example of a marshmallow here. I'm going to do this while I draw. If you take a marshmallow and you make it 3 times as tall as it used to be, it has been stretched. Or if you stretch it, it's 3 times as tall as it used to be. It could be 2, could be 7, whatever it is. But if you've put a number in front and you've multiplied it, then you've made it taller and thinner. So this, we would say, is a vertical stretch by a factor of 3. Now, you might have your guesses as to what the 1/2 is going to do for us, but let's put it in the calculator and find out. I'm going to change my 1/3 to be a 0.5. I'm going to have to redo my absolute value here. Math menu, number, put in an x. So 1/2 or 0.5x. There's my parent function. There's my new one. Notice that it's gotten wider. So I've taken my marshmallow and I have made it half of its original height. Well, if I make the height half as much as it used to be, the marshmallow has to get wider in order to accommodate that. So where I was at 1, I'm going to be at 1/2, and where I was at 2, I'm going to be at 1. Where I was at 4, I'll be at 2. So effectively here we've changed the slope to be 1/2. So that's what we call a vertical shrink or vertical compression. So I made my marshmallow half as tall. It has to get wider. I shrunk it down vertically. And the last example, we have a negative in front of the absolute value of x. So here I'm going to change my second example to have a negative, and notice that the negative is different from the minus key on the calculator. So negative math absolute value of x. There's my parent function, and there's my new function. It has been reflected. We don't use the term flipped over, we use the term reflected. And we need to be specific. This one has been reflected over the x-axis. I know that because the negative sign is outside of the function. If we put a negative sign inside with the x, it's going to reflect it over the y-axis. In the case of absolute value, it's not going to look dramatically different in most cases, but you need to realize that this reflection has gone top to bottom, so that's reflected over the x-axis. So reflected over the x-axis, and we can sketch that real quickly. The slope is still 1 and negative 1 on either side. So generically speaking, we can write all of these transformations in a format that looks like this. A times the absolute value of x minus h plus k. And all of these things do something particular to the graph. And in these examples, hopefully what you figure out is the k, the number outside, is a vertical shift. It moves the graph up or down. The h inside is a horizontal shift. It moves the graph left or right. And the reason it goes the opposite direction that you would intuitively think is because of this minus h. If it says x minus 2, then the h is really only 2 because the minus was already there. Therefore, it's going to the right. And the number in front gives you a stretch or compression, which we also call a shrink. A negative in front will give you a reflection over the x-axis. If you want some additional examples, I would suggest you look in your textbook at page 127, problems 5, 16, and 22, and we'll address more of this in class. Remember, your only task in the video is to take notes, come in with your questions. If you need to watch it again, please do so, but take the notes, come in with questions to class, and we will see you then.